All right, so I'm on the last one. So this one right here. Now, couple things they already said. So they said given that ABCD is a parallelogram and side AF is congruent to side CG, they want us to prove that AFE and CGE are congruent triangles. So they said that this entire shape is a parallelogram. So that means any property of a parallelogram applies. Since we know it's a parallelogram, that means any property that's about a parallelogram, so opposite sides congruent, opposite angles congruent, opposite sides parallel, etc., that's all fair game because we now know it's a parallelogram. They also said that these two little pieces of a side are also congruent. All right. And they want us to prove that this triangle right here is congruent to this one right here. All right. So, based off of where these triangles are, what's something that could be relatively relevant for us to know? So, look at what comprises these two triangles. All right. What are some of the pieces within this parallelogram that comprise these two triangles? Or what's something that may be important to know with this parallelogram at some point? So let's come up with a plan. So if we're proving triangles are congruent, that means we have to use one of the postulates. So that can be side, angle, 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 side, angle, side, or hypotenuse leg. All right, is hypotenuse leg possible here? No, these are definitely not right triangles. And there's no way we can prove they are. All right, so it has to be one of the others. Now, side's probably out as well because the F and G being congruent, that would be kind of hard to prove because it's not a diagonal nor part of the parallelogram itself. All right. So that leaves us with either knowing two angles in a side or two sides in an angle. All right. So you can approach this in a number of given ways. Does anyone have an idea how they approached it or what they started with that kind of helped them lead to the right track? What's some of the things that you stated that it said that it accepted? Okay. So BC is congruent to AD. That could work. All right. So these sides are congruent because opposite sides of parallelogram are congruent. Now, does that really help us in the long run with these two triangles, though? Not really, but you know what? Gives us a good thing to start with. What else could we say about parallelogram that we know of? So what are some other things we could say about this parallelogram that we know for sure is true? So guys, there's no wrong answers here. I just want to see what you know. Okay, let's try this. Are there any angles in this triangle between these two triangles that you can identify as congruent? Which, no, there are. There are, but where? So that's not in the triangle that I want. These two triangles. AF? AEF, good. So AEF, what's the other one? Say it again? CEG. Those are congruent. Why? So it's not alternate, but they do have a connection. So look at the shape. They're right here. So here and here. So what's like the general shape? So that may be where you look at that blue sheet that I gave you. They're vertical. So vertical angles are congruent. Now, bringing up alternate interior angles, that's another pathway we can take. All right, because what do we know about parallelograms? What's parallel? Not just two, but two sets of opposite sides are parallel. All right, so can't we state that we know that the opposite sides are parallel? Can we? Yeah. So which two sides are parallel? BC and AD are parallel because opposite sides of a parallelogram are parallel. We know that. What's the other two sides? AB and DC are parallel for the same reason. All right, now, since we know that stuff's parallel, now we can get some more congruent angles. So think about your parallel angle properties that show congruent angles. So again, look back at that blue sheet that I gave you. That'll help. Which two angles could we use a parallel line property to say that they're congruent? And I'll give you a hint. You may have to turn your computer to see it. Like physically turn your computer. Not 180, 90 degrees.
Oh, it said 360. Got it. That didn't do much.
I'll give you a hint. Alternate interior. I'm looking for a set of alternate interior angles. Think about what that looks like. Not those two. So guys, I'll give you a hint. I'm looking at these two parallel lines. So these two parallel lines and this transversal. So AC is the transversal. So these two parallel lines and AC is the transversal. You can do it. Come on. What are the two angles that are congruent by alternate interior? Say that one more time. Right. Three letters for angles. CEA. That's a side. AEF. That's the angle we already have. So you're close.
Is it just like in a different order?
You're close. Those are alternate interior angles on if the transverse is BD. I'm looking for the transversals AC. Come on, guys. Shh. BE. Not quite.
What about? Did we already do the A?
What about FAE?
Oh yeah, FAE and then GC.
There you go. All right. So the other one is FAE and GCE. FAE, GCE. Why? They're alternate interior angles. So now, do I have enough information to say these two triangles are congruent? Yes, no, maybe, kiss my butt, what? Yes, by what postulates? Nope, we don't have three angles.
Angle side.
Guys, you're just guessing. Come on. It's two angles and a side. Angle, angle, side, because the side's not in between them. So we can say that triangle FAE is congruent to GCE by angle, angle, side. So guys, listen. So you have to know these properties. All right. Now, I'm not going to listen to me. So I don't want to hear any lips moving. The two triangles are congruent by angle, angle, side. But you got to know these properties. Okay. Now, on the test, because you do have that Thursday, I'm not going to make you do a whole proof from scratch. What I am going to make you do is write out the reasons if I give you the statements. All right. You got to at least be able to logically tell me why that statement is true. If you can't, it's going to be issues. Okay. So, what I want to do now, before we get into the new stuff today, I want you guys to go to the other proof delta math, so the proofs with quadrilaterals. So we're doing the very first one. So proofs with quadrilaterals, the other 5.2. And I want to do the very first one together. So remember, this is the one that you have to do for homework. All right. So we're going to do one of these together, and then we're going to do something else. Very first one. All right. So is everyone here? Okay. First thing you need to do, graph these points. All right. Take a minute to plot these 4 points. So -6, -8. 1, -2. 3, 7. And -4, 1. And then once you graph all 4 points, it graph quadrilateral. So it should look like this when you graph it. So again, you're graphing these 4 points. Yes. Very first one on 5.2, proofs with quadrilaterals. (5.2) proofs with quadrilaterals. I assigned it to you yesterday. That's the one that you had to do on your own. So, now, this is not necessarily a proof, but you kind of still have to reason your way through it a little bit. Okay? So they want us to show that this quadrilateral is a rhombus. What do we know about rhombuses? What's true about a rhombus? Technically, a square is a rhombus. Yes. It's what? The diagonals are perpendicular. That's one way. What else? What's kind of the defining feature of a rhombus? 4 congruent sides. So I will prove that this quadrilateral is a rhombus. Let's look at our So the only thing that we got is that works will be all sides of equal measure. Now, they want us to then show, hush, I'm basically giving you this answer. They want us to then show that these are all congruent. So here's how you do that. So, there are two ways you can do this. You can do this either using distance formula, which I do not recommend, or Pythagorean theorem. So, I'm assuming y'all are going to want to use Pythagorean theorem because it's easier, like way easier. What is the Pythagorean theorem? A squared plus b squared is equal to c squared. All right. Now, what I mean by using Pythagorean theorem, you want to do rise over run from each point on every side, and that'll create a right triangle. So what's my rise over run from N to O? So here's my rise. We go down. And then my run is right here. So if you notice, that creates a right triangle. But what would these side lengths be? It's what? So 2 is here. What's here? 9. So can't we solve for this side length using Pythagorean theorem? Yes, we can. So this would be 2 squared plus 9 squared is equal to c squared. What's 2 squared? Guys, I need everyone looking at me. All right. I'm trying to show you this. This is actually on your homework. What's 9 squared?
81.
What's 4 plus 81?
85.
85. Equals c squared is my last step for solving.
Square rooted.
Square rooted. So because they want an exact answer, I'm going to leave this as the square root of 85. All right? This is the square root of 85. So that means that this is a rhombus. We have to get square root of 85 for the other 3 sides. All right? So let's check from M to N. So if I do rise over run from M to N, what are the dimensions of my triangle?
9.
No. Guys, I know you know how to count.
3, 6,
7.
It's what?
7.
I think.
So 6, then 7. Guys, it's just counting. Just how many units up and how many units across. I know y'all know how to count. Good Lord, you wouldn't have passed kindergarten if you didn't. Well, that's what you problem. Anyway, so 6 squared plus 7 squared is equal to c squared. So what's 6 squared? 36. 7 squared? No. Guys, what's 7 times 7?
49.
Okay, wait. Guys, the fact that you're not taking this seriously is ticking me off. I'm literally showing you how to do your homework. So, 36 plus 49, what is that?
85.
85. So then I take the square root, I still get the square root of 85. Now, if I check the other 2 sides, what you're going to run into is that this will be 9, this will be 2. Well, guess what? We don't have to do the Pythagorean theorem again because it's the same dimension, square root of 85. Same thing here. This would be 6, that's 7. Square root of 85. Don't even have to do it. You only had to do it twice in reality. Because then if you check the rise over runs, they're the same thing. So we can state that these are all the square root of 85. So that's literally what you're going to type in for all four of these. And then we can say that all sides are of equal measure. Therefore, the quadrilateral is a rhombus like we want it. Any questions on that one? One last thing I want to do before we move on to the new stuff. So after you finish inputting that, I want you to clamshell your Chromebook. So once you finish inputting that, I want you to clamshell your Chromebook. So you should have out all of your graphic organizers and that journal entry. You should. So here's what we're going to do. Using all of your graphic organizers. So the yellow one, the salmon one, the pink one. Well, not the yellow one. The pink one, the salmon one, the blue one. Those are the three you want. We're going to go through. I'm going to call names. And I want you to tell me the reasons that these are true. So you better be paying attention. So you're going to want that journal entry out. Because this one specifically, so this part of your Delta math, you got to know how to do. Because that's going to be on your test. That is what's going to be on your test. So if you weren't here, I don't mind if you pull it up on Canvas, but that's it. All right, so I got the popsicle sticks of destiny up here. All right, so to start us out, let's look at what we're actually trying to prove. So, given ABCD is a rectangle and AF is congruent to DG, they want us to prove that EB is congruent to EC. So, this whole shape is a rectangle. And these two little baby parts are congruent as well. Now, they first said that FG is congruent to FG. So the same side is congruent to itself. So why is that true, Dominic? What tells us that's true? Reflexive property, good. Now, from there, they say that AG is congruent to DF. So AG is congruent to DF. All right. So why is that true, Dylan? So I'll help you reason through this a little bit. Is this little baby segment congruent? Is this segment congruent to itself? And isn't that like the sum of these two segments? So why would these two be the same? Aren't these like, two congruent segments being added together?
Yeah.
So wouldn't that make sense? So that's the reason. That's one that we didn't go over. That's why I was helping you with that one. So congruent segments added to congruent segments makes them congruent. Then they say angle A is congruent to angle D. Why is that true, Aiden?
I'm gonna have to go with
So not reflexive property, they're not in the exact same spot. But what's the shape? What do they tell us that shape is? So Aiden, it says it up top. What do they say that is?
Oh, it says that it is a rectangle.
What's true about a rectangle?
They had 90 degrees.
And aren't 90-degree angles always going to be congruent to each other?
Yeah.
Yep. So that's the reason. So all in a rectangle and square, all angles are congruent. Then they said AB is congruent to DC. Why is that true, Autumn? Well, look at where they are. They're opposite. Opposite sides of a rectangle are congruent. And they told us it's a rectangle, so we can use that fact. So now, So now they're saying that these two triangles are congruent. So what postulate tells us that? So look at everything that we've marked so far. So I'll leave that on there. So why are those two triangles congruent? Here. Zoe. What makes these two triangles congruent? What postulate? Side angle side. Good. So that means these two angles are congruent by what, Abby? So we just proved the triangles are congruent. So why can these angles be congruent? Aren't they part of the congruent triangle? So what kind of reason tells us that they can be congruent to each other if they're incongruent triangles? It's an acronym. CPCTC. So corresponding parts of congruent triangles are congruent. Basically, if you prove triangles are congruent, you can say any part of them are also congruent as long as they're corresponding. Now, Now, they're saying that these two angles are also congruent. Why is that true? Let's go. Jonathan, why are those two angles congruent? Oh, sorry, Jonathan M. Not technically, because these angles are technically not part of the triangle, but they are part of another shape. What's the overall big shape? Rectangle. So both those angles will equal what? 90. So again, it's just because all angles of a rectangle are congruent. Then they said that these two baby angles are congruent. Why does that make sense? So we know that these angles are congruent. We know that the overall big angles are congruent. What's the connection between these two baby angles? They're what? Anyone? What's the name for these two? Complementary. So, in other words, if two angles are complements, that means they add up to 90 degrees. So, in other words, if we subtract congruent angles from congruent angles, we get congruent angles. Thus, why are these two sides congruent? What type of triangle is this? What type of triangle is this? Nope. It's isosceles. Why? It has two congruent sides, two congruent angles. But we had the congruent angles first. So remember, in isosceles triangle, if you've already shown that two angles are congruent, the sides opposite those angles are also congruent. And that's what you can say here. So where is it? In triangle, sides opposite congruent angles are congruent. And that'll be it. Now, I wouldn't give you one that hard. So let me find one. I said on the test. You're good. Okay, let's do that one. All right, let's try this one together. One more and then we'll move on. So they said that these two triangles are congruent. They said that these two sides are congruent. And they said that B is a midpoint. And they want us to show that ABCD, or this overall shape right here, is a parallelogram. So think about what we need to show to prove a parallelogram. So that's where your pink sheet is involved. Now, they then said that AB, so this baby segment right here, is congruent to BF. Why can we say that given the information that we have? Anna. And she's at the bathroom. Okay, Shaki, why can I say that? What did they say previously that I can make that assumption? It's not because we add them, but it comes from something up here. It's the midpoint. So, and what does a midpoint do, Shaki? It cuts it in half. So that means that a midpoint divides segments into two congruent segments. They then said that these two are congruent. Why can I say that? So what statement up at the top leads me to that answer, Davis? So there's something up here that lets me say this. So what statement up here could possibly lead me to this statement? Which one of these three? That these two triangles are congruent, that these two sides are congruent, or that this is a midpoint? Not necessarily those two sides. Look at where these sides are, and then look at what I'm hovering over. Nope, we already used the midpoint. So the congruent triangles. All right. So we proved congruent triangles. So why can I say two sides of those congruent triangles are congruent? It's that really long acronym. C.
I know what it is.
Just go for it, even if it's just say it. CP. CPCTC. I'll take mercy on you. Now, these two sides are incongruent. Why? Let's go Marley. So let's think about it this way. We said these two sides are congruent. We said these two sides are congruent. So why can I say that those two are congruent? Isn't it just like, didn't we just kind of switch these out? So what's that called? It's on your blue sheet. So when you just switch them out. I think it's the one after it or before it. I can't remember. It's transitive. It just means that you flip flop because they're all, or substitution. That works too. I'm going to say substitution. So why is this a parallelogram now? Let's go out here. JJ. So I've said that these two sides are congruent. I've also said earlier that those two sides are congruent. So why can that make a parallelogram? Specifically, what sides? Starts with an O. opposite sides are congruent. So it's a parallelogram because it's a quadrilateral where it has two pairs of opposite sides congruent. And that's it. All right, enough of that. Okay, so here's what I want you guys to do next. So back into your Chromebook. All right, I want you guys to go to Canvas. There's two things I need from you, so listen up because I don't want to repeat myself. So what I want you guys to do is go to Canvas, go to my announcements, and click on the link that says GeoGebra Activity. So go to Canvas, my announcements, GeoGebra Activity, and then click on the link that's within it. I also want you guys to take out your packet and go to page 11. So take out your Unit 5 packet and go to page 11. So get that link open and then take out your packet. That's what I need you to do right now. Yes. Hmm? Yeah, you don't have to sign in. Guys, I don't care if you sign in or not, just put your name. So it's going to ask you to continue with sign in. You don't have to sign in, just put your name. So don't freak out. We're doing this activity together as a class. I just want you to have that manipulative open. Where is this? Announcements in Canvas. You'll be fine. All right, guys. Has everyone got their website open? And you also on page 11 open on your. So you want page 11 open in your packets. All right, so here's what I want you guys to do. Okay, we're gonna work through these together, but you guys are gonna talk with me through this. So our next lesson is all about triangle centers. So we're moving away from quadrilaterals a little bit and going back into triangle land. All right. Now, triangle centers are just something that just happens when you intersect specific segments within triangles. So we're actually going to play with it a little bit. All right. So what I expect you guys to do is, as I'm doing this, you need to be doing it as well to make your own discoveries. So here's how you're going to use this. All right, I'm on full screen on my end. I recommend that too, so you don't have to worry about, unclicking things. Now, I would unclick the one that says inner triangles at the bottom. So, the first question, we're just going to walk through these together. The first question says, which of these centers stay inside the triangle at all times? So, the centers, all right, are these: centroid, orthocenter, incenter, and circumcenter. Now, as of right now, all four of them are inside the triangle. But what I want you to do is you can actually move these points around. So move these points around and see which ones will always stay inside. All right? So take a minute, try it. And then when you think you got an answer, write it down for number 1 on page 11. So which centers always stay inside the triangle?
I don't appreciate it. Do you appreciate what?
All right, you guys got an answer? You just need to write down which two centers, there are two of them, that always stays inside the triangle, regardless of where you move it.
The ortho center. Nope. Still
It would help if you had the thing open.
it's, yeah, central intercenter. Yeah, I tell them. It's still on there. It's still on there. I'm leaning on to these guys. My friends.
All right, so what'd you guys get? Centroid and end center, good. So on your packet for number 1, you're going to write centroid and end center. It's in Canvas announcements. So, shh. Guys, please stop talking. So for number 1, you're going to write centroid and end center. Now, based off of your observations, does that mean that this triangle is acute, a right, or obtuse? So what makes an acute triangle?
More than 100.
All the angles are acute angles, meaning less than 90. What makes a right triangle? You have to have what? 190-degree angle. What makes an obtuse triangle? One angle that's over 100, one angle that's over 90, not 180. All right. So if I go back to this picture, all right, what does it look like? So what do these angles look like to you guys? Do they look like they're going to be acute angles, obtuse angle, or right angles? Definitely acute. All of these are definitely acute angles. They don't even look close to a 90. Whereas if I make them wider, that's when they start going outside. Make them thinner, they stay in. So we want a acute triangle. Now, where is the location of the orthocenter when it's formed into a right triangle? So before I do that, I need to get some angle measures. So here's what I want you guys to do. So watch me carefully. We're going to do this step by step. First things first, I want you to go up here and click on this little button that has the angles. All right, it's at the very top of the screen. So you got to look above the board. You're going to click this and click angle. Now, here's what you're going to do next. So up here, click it, click angle. And what you're going to do is we're going to put angle measures for all three. So watch me carefully. So I'm going to click point C first. Then I'm going to click point B. And then I'm going to click point A. Of course it did that. Okay, I lied. So to get rid of that, I want you guys to click it. So click the mouse key again. Click the mouse key over here. Click this angle. And then hit the backspace. So click like the little circle angle marking and hit backspace. Hit Control Z. Control Z. So just that green marking.
Yeah.
All right. So I labeled it wrong. I always got to test this out. So hit the angle key again. Click angle. All right. I know what I did wrong. So hit A first, then B, then C. So
Is it supposed to look like I can't move it? Like so just make sure you're going.
So guys, just make sure you're going.
What? Let me send you.
All right, now. So guys, make sure that your points look a little bit like mine. So A's here, B's here, C's here. Now, I'm going to keep the angle key clicked. And I'm going to hit now B, C, A. And then finally, I'm going to hit C, A, B. And you should have all three angles marked now. Now, if it's not perfect, it's okay, but we do have to move on. So, make sure you hit the mouse key again at the end. Otherwise, you can't move it anymore. Now, it's talking about the orthocenter, so I'm going to click off every other center except the orthocenter because that's the only one I care about. Now, they want us to make a 90-degree triangle. So here's how I recommend it. Do you guys, it's hard to see on my end of the board, but do you guys see on your screen how there's a grid? Take two of the points and line them up with points on the grid on the same line. So I'm going to move A and B so that they line up. And then you're going to move C to line up with A on a point on a grid. So you notice that you have a right angle right here. So where did the orthocenter end up on the right angle? So where did the center of the orthocenter go when I make a right angle? It went on top of A. So in other words, it went on top of the right angle. So what we would say here is that this would go on top of the right angle. All right. Now, which triangle centers are always collinear? Collinear means always on a line. And the line that we're going to use is called the Euler line. So, up at the top, do you guys see where it says Euler line? Like there's a checkbox that says Euler line up at the top. Check it. And then check the other three centers. So centroid, incenter, and circumcenter. Now, move the triangle around and see which centers will always stay on that line regardless of where you move the triangle. So, write down which centers. So, which three centers are collinear? I mean, they stay on that Euler line. The orthocenter, the centroid, and the circumcenter. Now, number 5, we're going to skip. I'll tell you what it is. So in other words, if you make an equilateral triangle, meaning all three sides are exactly the same length, and you have 60-degree angles for all three angles, what happens to the centers is they overlap in the exact same spot. So all four centers will end up in the exact same spots. Now, let's look away from the centers for right now. And now we're going to look at the lines. So I'm going to click off the Euler line, and I'm going to click off my centers. And they asked me to see which lines go through my midpoints. So I'm going to click on my midpoints. So that should give these little green dots when you click midpoints. Now, the lines they asked for were the altitudes. So I'm going to click that. The medians. The angle bisectors. And the perpendicular bisectors.
I can't make my Chromebook. Were you able to, did you grade them already?
Huh?
Did you grade the Chromebooks already?
The journals, you mean? Just put it on my desk.
Oh, no, I already did. I was kind of asking if,
They're graded.
I guess.
All right, so we're looking to see which of these will always go through the midpoint. So I'm going to look at one at a time. So let's talk about this together. So I'm going to look at medians first. So if I move this around, do my medians always go through the midpoints? Yes or no? Yes, they do. All right. I'm going to check altitudes. Do the altitudes always go through the midpoints? Are the altitudes going through those green dots? No. Angle bisectors. You're welcome. Do my angle bisectors always go through the midpoints? Yes or no? No. Shh. Perpendicular bisectors, do they always go through the midpoints? Yes, they do. So, the two that always go through the midpoints are my perpendicular bisectors and my medians. So guys, there's a method to this madness, all right? If you're not understanding what the heck is going on, just enjoy the ride, all right? And just write down what I say because we'll get a lot more explanation in just a minute. Now, we're going to view only the altitudes and the perpendicular bisectors, and we're going to ask what are these lines have in common. So if I go back here, I already got the perpendicular bisectors on. Now I'm going to also turn on the altitudes. So looking between the blue and the pink lines, what's something that you notice that is true for both of them? Not parallel. They're always perpendicular to what? Aren't they perpendicular to sides of the triangle? At some point? Yes, no, maybe? Yes. So that's what they have in common. They're perpendicular to the sides of the triangle. All right. Now, then it asks, what is the circumcircle and how does it relate to the triangle? So I'm going to click all my lines off now. And I'm going to click I'm going to leave midpoints on. But I'm then going to click the one that says circumcircle. So that's right here. So I click the one that said circumcircle. Now, what's true about this circle? What's it doing? How does it relate to the triangle? It's going through all the vertices, right, of the triangle? Yes? Yeah. So that's how it relates. The circumcircle goes through all the vertices of the triangle. All right. Now the inscribed circles. We're going to click off circumcircle and click inscribed. What's true about the inscribed circle? So what's true about the sim-scribe circle? So it doesn't necessarily go through the midpoints, but isn't it kind of contained inside of the triangle? Yeah. So in other words, it's contained inside the triangle at all times. All right. And with that, we're going to move on. Okay. So, no. So go ahead and close your Chromebooks completely now. And take out that yellow paper. So, I'll be right there. Don't worry about that. It's not a grade. It was just to look into stuff. Yeah, it's not a grade. Okay, so why did I make you go through all that mess with no point to it? Well, there actually is a point. So, like I said, centers of triangles. This is the last lesson that we have in this unit. So, centers of triangles are all formed by different parts of the triangle. All right. Now, these are my 4 centers, which we already talked about: circumcenter, incenter, centroid, and orthocenter. Now, all of these centers, guys, quit messing around. So all of these centers, which are where these specific lines overlap, but those specific lines have names. So the first one is circumcenter. So I'm going to show you guys what this looks like on here. You don't have to do this, but I'm going to click the circumcenter. All right. Now, I'm going to also click the 4 different lines that they create. So I'm going to click the medians, the altitudes, the angle bisectors, and the perpendicular bisectors. Which of these lines form the circumcenter? So which of these lines, when they intersect, form the circumcenter? So is it the medians, the altitudes, the angle bisectors, or the circumcenter, or the perpendicular bisectors? So blue is perpendicular, orange is angle, pink is altitudes, green is medians. So which one? The perpendicular bisectors. So if I click off all the others, do you guys see how whenever these perpendicular bisectors, where they intersect, that's where the circumcenter is? That's what it's talking about. So these are created by the perpendicular, guys, please stop talking, bisectors. Now, we already know what a bisector means. What does a bisector mean? It cuts the side in half. So that means that these perpendicular bisectors cut each triangle side in half. So X, Y, and Z are the midpoints. So X, Y, and Z are midpoints. That's why it's marked as congruent segments here and here. Now, some other things to note. The perpendicular bisectors, or no, not the perpendicular, the circumcenter is equidistant from each of the sides of the triangle. Wait, the sides or the vertices? Nope, I lied. It's the vertices. Circumcenter. So the circumcenter is equidistant. The circumcenter is equidistant from each of the vertices of the triangle. And the reason for that is the circumcenter is actually the center of the circumcircle. So this is going to be a terrible circle. But if I drew a circle where, remember, they go through all the vertices, the circumcenter is actually the center of that circle, meaning that each of these lengths from the circumcenter to the side is known as a what? So if I go from the center to the side edge of a circle, that's called a what? Starts with an R. Radius. So that means that all three of these are the same length. Now, another thing to note, all right, perpendicular bisectors intersect the sides at a 90-degree angle and go through the midpoint, or the midpoints of each side. So that's how you can tell if it's a perpendicular bisector. It's hitting that side at a 90-degree angle and it goes through the midpoint. Now, the next one is the incenter. All right. So I'm going to go back. Watch it. I'm going to go back to here, and I'm going to click incenter. Now take a guess. Which line do you think the incenter is going to go through? So we have the medians, the altitudes, and the angle bisectors left. So medians, altitude, angle bisectors. So which do you think the incenter is going through? The angle bisectors. So if I click these off, it does in fact always go through the angle bisectors. So it goes through the angle bisectors, ladies. What does it mean for an angle bisector? What does it do? Well, it bisects the angles, so it bisects these vertices, but what does that mean? It cuts the angle in half. So the angle bisectors cut, y'all, seriously? Cut the vertices, dash the angles of the vertice in half. Now, another thing to note, the incenter is equidistant from each side of the triangle. So if you drew a straight line from the incenter to the side for all three sides, all these segments would be congruent. Now, another thing to note, are X, Y, and Z midpoints in this case? So for the answer is X, Y, and Z midpoints. They're not. The reason why is because these are not labeled as congruent pieces. The incenter does not always go through the midpoints, which we found out earlier. They do, however, the inscribed circle is what actually forms the incenter. The incenter is the center of the inscribed circle. Now, the centroid. So, with the centroid, only thing we have left could be medians or altitudes. So here's medians, here's altitudes. Which one does the centroid go through? The medians. So, the centroid is created by the medians. Now, look at what X, Y, and Z are. What's X, Y, and Z? They're midpoints because we have congruent segments on either side of them. So the median always goes through the midpoints. It's basically, a median is when you draw a line from the vertice to the midpoint. That's what it is. Now, doesn't necessarily hit at a 90-degree angle. All right. But, so a median is created by a vertice connected to the midpoint of the opposite side. Now, medians are, it's a little bit weird. Okay. So, with medians, there's actually a rule. So, it's called whole, small, and large pieces of the segment. And I'm going to state the rules, but just know it's a little weird. So, the small segment is equal to a third of the whole. So in other words, if you divide the length of the whole segment by 3, that's the length of the small segment. The large segment is equal to twice the small. All right. You can also say that the large segment is equal to 2/3 of the whole. So that means if we want to write the whole in terms of the small, the whole is equal to 3 times the small. Now, what does all this whole, large, and small mean? Well, if we look at each median, okay, the whole, let's just take AY for example. This is one median. The whole is the whole segment. So this would be the whole. The small would be the one that looks smaller. So the piece on one side of the centroid that looks smaller, that's your small segment. On the other side, the longer of the two, on the other side of the centroid, that's your long segment. Or your large. I said large, not long. So occasionally you will find side lengths for those. And these are the formulas. So in reality, as long as you remember the whole is 3 times the small, the large is twice the small, you can pretty much find all of them. The small is just kind of the middleman. Now, the last one, orthocenter. That is created by altitudes. Now, an altitude is created by a vertex connected to the opposite side so that it is perpendicular to that side. So an altitude is when you start at the vertex and connect it to a side so that's perpendicular or forms a 90-degree angle. Now, Orthocenter is easy because we don't deal with them that often. So there's no special features. The only thing you would have to know is that altitudes form an orthocenter. That's the only thing you gotta know about that. So like if that was like a multiple choice question on the test, if I asked what special line forms the orthocenter, you would say altitudes. That's all you have to say. Features. Now, the back side of this just kind of goes into more detail about everything. We're not going to go through that. It's just basically a restating of what we already stated. Now, got about 10 minutes left, so I'm going to do at least 1 or 2 problems. All right, we'll do some more tomorrow, but I at least want to get through 1 problem. So the one that I want to do is one that's a median. So let's go back to your packets. And I want you guys to go to page... Center. There we go. I want you guys to go to page 15. I'm looking at the bottom of page 15. Page 15 in your packet, the bottom. I just want to do one of these. And we'll do like 1 or 2 more tomorrow. All right. Because I know we did this kind of fast today. So, it says that in triangle ABC, we're given the centroid. AD is 8, AG is 10, BE is 10, AC is 16, CD is 18. And they want us to find each length of the remaining segments. So what I tell students is always go through, mark what you're given first. So AD, they already marked for us. They said that's 8. AG, they said that's 10, which they already marked for us. BE, that is also 10. AC, so this entire segment right here, is 16. And CD, this entire segment right here, is 18. Now, we know the centroid is formed by what lines? What type of lines is it? What lines did I say the centroid is formed by? The medians. So we're going to go through and find the rest of these. So we're going to start with DB, which is right here. Knowing what we know about medians, what's true about medians? Medians are lines that go through the what? The middle of each side, so the midpoints of each side. So that means that points D, F, and E are midpoints. So given that that's true, what's the length of DB? Nope.
5.
Stop guessing. 8. Why? Why is it 8?
Ah.
Right, the midpoint cuts it in half. If this segment's 8, this segment's 8. All right. CG, which is right here. So this is on one of the medians. And they told us the whole median is 18. Now, so that means we're using one of those formulas. Does that appear to be the larger piece of the median or the smaller piece of the median? The larger. All right. So let's start by finding the smaller piece first, which is GD, which is right here. It's also on our paper. So a lot of times it's easier to find the small first before you find the large. Because what's true about the small? It's what to the whole? Well, no, duh. In terms of length,
1/3.
it's 1/3 of the whole, which means, how would you find it?
I looked at my notes.
Mm-hmm. So if the small segment is 1/3 of the whole and the whole is equal to 18, what's the length of the small? 6. Why? 18 divided by 3, 6. So this is 6. So GD is 6. So all we did was 18 divided by 3. Now, how does the small connect to the large? The small is what to the large? So the large is twice the small. So that means, what would be the length of the large? 12. 6 times 2. Now, is it true that 6 plus 12 equals 18? Yes. So we did it correctly. That's how you go about these guys. Does that make sense? All right. So, we ain't done. Did I say pack up? Oh, heck no, I did not. I don't care. So, we're finishing this problem. So, now we got GE. So, GE is right here. We were given the larger piece, and that's the smaller piece. So, that means if the large is twice the size of the small, what's the length of GE? So, this is the larger piece. This is the smaller piece. If the large is twice the small, what's the length of GE? 5. All right. BC. What's the length of BC, do you think? So don't we have a piece of one side of the midpoint? 20. Because this other side should be 10. So BC's 20. EA. We can just add. So EA. We already found the small piece to be 5, the large piece to be 10. So what's the whole piece? 15. BA, what's the length? 16. And then finally AF. So if the AC is 16, that means AF is what? 8. There you go. Now you can pack up. Now, there is both a Delta Math and a quizzes on this. We'll do a couple more of these tomorrow. Don't forget, test is Thursday. Uh-huh. This unit's short.
Hey!